Hi there, I'm Tiffany from SigOpt. Thank you all for joining us today. This is the first session of our monthly quant series, Tuning for Systematic Trading. We will be hosting these series the third Tuesday of every month, and they will focus on 3 topic areas tailored to different interests. First is research. SigOpt is unique among software providers in that we have an active research team that explores new optimization and AutoML techniques, consistently writes papers for NeurIPS and ICML, and has developed a patented system for parameter and model tuning. In some sessions, we will share underlying insights from this research. Second is modeling workflow best practices. We work with enterprise customers across 6 different industries and academic users that span dozens of other domains. This collaboration has given us a unique perspective on best practices for the modeling workflow. The final topic is use cases. Sometimes it is better to show rather than tell. In these presentations, we will focus on how we solved a specific modeling problem. These typically include code repos, so you could recreate the work. We take customer privacy seriously, so these are most often toy rather than specific to an individual user. To kick off our series, today we will give an overview of Bayesian optimization and how to use it to tune a single or multiple metrics and to gain additional insight on your modeling problem in the process. Joining me here today is Tobias Andreessen, a machine learning engineer who supports a number of our systematic trading customers. Toby will lead this session. We have some time scheduled at the end for Q&A. If you have any questions throughout the session, please feel free to submit it through the Q&A box and we'll get to it at the end. Now I'll have Toby take it away.
Perfect. Thank you so much. And hey, everyone, thank you for joining. I know these are hectic times, so I really do appreciate that you take your time out of your calendar to join us for this webinar. So what I'll be talking about today is some of the intuition that goes behind Bayesian optimization, and talk about how to expand this into multiple metrics, and why that makes sense hopefully becomes clear through the talk. I tried to put together an abstract for the presentation, which is essentially SigOpt provides an extensive set of advanced features which helps you, the expert, save time while increasing model performance via experimentation. Today, we'll start out this talking series by giving an overview of general black box optimization, efficient Bayesian optimization, and end up extending this to multiple competing metrics. So again, as Tiffany said, this is going to be part of a series, and what I'll try to do today is lay the foundation for the things to come, so that people can kind of be on the same side, and have an idea about what it means when we say Bayesian optimization, a black box optimization. So again, the motivation is that we'll start out with an overview, very short overview of SigOpt, then we'll talk about black box optimization in general, and then talk about how to expand this into multiple metrics. So again, at SigOpt, we have a vision, which is to accelerate and amplify the impact of modelers everywhere. So our job is essentially to build software that helps you amplify your work. So we've built a solution, or rather a platform, which consists of 3 main components. The first of these components is the experiment insights, which essentially allows you to track, analyze, and reproduce models in order to improve your productivity and your modeling workflow. The second component is the optimization engine itself, which is what we'll be talking about today, which is essentially what allows us to help you amplify your work. And the third component, or the third pillar, is essentially the enterprise scalability, because we're not limited to anything when it comes to infrastructure, libraries, etc. All the things we do runs through a REST API, which essentially means we're never touching your data, we're never touching your models, and we can run any sort of system that you have in place. So as I said at the beginning, we've built an extensive set of advanced features, and that's some of the things we're going to cover over the next few months. In the interest of time, today we'll only be digging into the optimization engine itself, and expand that scope into multimetric optimization, because as you can imagine, for most modeling tasks, not a single metric represents success. So the next thing we'll talk about is essentially what is black box optimization. And black box optimization is not necessarily Bayesian optimization. There is a lot of ways to do it. But the first thing to do is essentially to ask, why should one do black box optimization? And I'm probably a bit biased when I say that, all problems in life can essentially be thought of as a black box problem, and the goal is just to optimize it. That's not really what we'll be talking about today, but what we'll be talking about is essentially how to look at your modeling problems through this black box lens. And some of the reasons why you should do this is kind of ties back to our vision, which is to amplify and accelerate your modeling, which means that we want to amplify the performance of your models. We also want to help you, just be faster, bring more models to production. And for a lot of our customers, some of the issues is tied to identify resource constraints, whether it sits with the modeler, it sits with the infrastructure. And we're trying to help solve some of those problems through the lens of black box optimization. So that's what we'll be talking about today. So how should one think about these black box problems? As I mentioned earlier, we don't touch your data. We don't touch your models. That's why we have this firewall down the middle. Essentially what you see on the left is, that's all you. You have your data, you have your models. We don't really care if it's machine learning models or it's back tests. All we care about is that you're able to evaluate these models in some way that you trust. Maybe it's on a holdout set, maybe it's through backtest simulations. Again, you're the expert. We're just trying to amplify your work. So again, on the left, that's all you. On the right, what we're showing here in this picture is the SigOpt API. Again, this could be other ways of solving black box problems. But again, what you see on the right is the SigOpt API. And what we need from you and why we call this black box optimization is essentially because what we need from you is to define what are the parameters that goes into your model. And when I say parameters going into your model, I'm not talking about sort of these convex problems where I believe a lot of people listening in here have a pretty good understanding of what convex optimization means. That's not the problems we're trying to solve. We're trying to solve these problems where you do not have the ability to make underlying assumptions about your modeling. So these things could be, again, a neural network. How does your learning rate and the number of layers interact, and how does this help you get the best performance? That is essentially the problem we're trying to solve. So when I say you give us access to the parameters, I essentially ask of you to give me information about like learning rate, number of layers, number of nodes, and say, hey, I as an expert believe that my learning rate can sit somewhere between 0 and 1, or close to 0 and 1. And I can have somewhere between 10 and 100 layers. That is the information that you should ship to us. You can obfuscate this in any way. Like, all we care about is these spans, or it can be categorical parameters. So that's information you send to us, which essentially forms this black box. Our job is then to figure out where in this black box is the optimum for you. And the way we do that is going through this kind of feedback loop. And again, this is general to all black box optimization approaches. But again, we will say, try out this configuration of parameters, put it into your model, train your model, test your model, do some sort of evaluation that you trust, return the metric back to us. Then we will give you one more suggestion, and we'll go back and forth in this feedback loop. I hope this makes sense. this kind of lays the foundation for what we'll talk about next. Again, we tend to call this hyperparameter optimization because at the end of the day, all of these parameters that you can't really determine how they kind of form the underlying functions is typically called hyperparameters. But a lot of people, think about this in different ways. Some people talk about deep learning architecture search or hyperparameter search. In my opinion, all of these things are the same. Essentially, you have a set of parameters. You do not really know how they interact with each other than what you can observe. And what you can observe is what we will use to guide you to the best possible configuration so that we can help you amplify your models. And again, this does not have to be machine learning. This can sit on top of your convex optimization problem and help you come up with the right configurations for the parameters going into your convex optimizer, not solving the convex problem itself, but there is a lot of regularization terms, and we can help you figure out what are the best ones here. So as I talked about, there is a lot of different ways to solve these black box problems. And I'll go over some of them really quick, and then we'll talk about what we do at SigOpt. One way to think about it is through manual search, where essentially you'll leverage your expertise. Only problem is this is not very scalable. You have something like grid search. Super, super simple. It's very efficient in small problems. The only problem is it's not very scalable and it becomes infeasible pretty quick. Random search, super, super scalable. Only problem is you're kind of wasting a lot of knowledge in the sense that you sample a lot of points, but none of these points guide you to better decisions in the future, which is kind of a shame. Then we have something like evolutionary algorithms, which is great. The only problem is it's very, very resource intensive, and it kind of makes some assumptions about everything taking the same time, etc., which is very often not feasible. And then we have what we do. Essentially what we do is Bayesian optimization, which is essentially just another way to solve these problems. We have just chosen this approach because we find it a lot more efficient than these other approaches. And what I mean by efficient, I'll talk about later. But one of the problems here is essentially that it's super hard to parallelize. That's something we do. Like, we allow you to run 100 different machines at the same time, so 100x parallel. It's one of the beauties of running a distributed system. How we do that, I won't cover today, but in 2 months' time, I will be talking about that specifically, if that's of interest. So please keep that in mind. So Bayesian optimization and why this is more efficient and effective than other approaches. I like to call it sequential model-based optimization, because that's probably a more accurate statement about what it is. Think about this situation. Let's assume that we have gone through this feedback loop 5 times. That's the 5 yellow dots you see here. Essentially what we do is then build a statistical model, which we believe roughly represents how these parameters that you're trying to optimize represent the response surface, which can, for simplicity, think of it as being a learning rate versus your accuracy. So this statistical model is kind of our idea about how the world looks. But again, our job is to constantly build better statistical models. So how do we do that? The way to do that is essentially to figure out, hey, what is the next best point that we should ask you for? And what the next best point is, essentially means a lot of things. In this situation, we're simply saying, where do we know the least? Because think about it. Where we know the least is essentially where we will also learn the most. So it makes a lot of sense to ask for that point. So hopefully you'll turn that point back to us through this feedback loop. Now we can build a new statistical model, which is hopefully a little bit better than the previous ones. And the reason why we call this sequential model-based optimization is because now we do the same thing all over again and constantly ask for the point where we'll learn the most. That's not entirely true. And in a second, I'll tell you why. But again, I hope this gives everyone a bit of intuition about what's going on. Only problem is, what is the right statistical model? And this is where it becomes tricky. And this is where you see the beauty of running a distributed system. Because these statistical models is built by something called, in a lot of situations, built by something called Gaussian processes. The only problem is there is an infinite amount of Gaussian processes, so which one to choose? Here is 4 different examples. Again, it's the same 5 data points. It's just 4 different processes. And as you can see, they give very, very different results. And those very different results will have an impact on what you see at the end. The same goes for the acquisition function. As I talked about, we are constantly trying to figure out where we can learn the most by figuring out where is the biggest uncertainty. Now, the problem is that's only half of the problem, because if we are constantly doing that, if we constantly, let's call it exploring, if we constantly exploring, if we find some peak, we will most likely not be looking at that anymore, because why should we? We have already learned there's a peak. And that is not the problem you're trying to solve. You're trying to solve the problem where you find the top of this peak, which is why we are switching between what is known as exploration, where you're learning about the space, and exploitation, where you're narrowing down on the peak. And there isn't really a kind of hard line between what is what, or like when you should do what. But again, that's one of the trade-offs that we help you make. Kind of switching between these exploration and exploitation, because when you're doing exploration, you're simply saying, where do I know the least? Under the assumption, this is where you learn the most. Whereas when you're doing exploitation, you're saying, hey, which point in space has the highest probability of being better than what my current best point is? And how you're making these decisions are controlled by these acquisition functions. Again, as before, we showed there is a lot of these different Gaussian processes or kernels that you can choose. There is a ton of different acquisition functions, which will all get you to sample different points. That's what I'm trying to represent down here at the bottom, where each of the colored line is its own acquisition function, and where it has the highest peak is the next point you'll sample. So now, as you could imagine, if you were just going to do Bayesian optimization out of the box, you're no longer trying to find the right hyperparameters for your model. Now you're actually trying to solve a problem, which is finding the right hyperparameters for your optimizer. And I'm not sure that's particularly easier, which is why we built SigOpt, because all of these things is built into the SigOpt REST API. We will constantly be doing the trade-off between exploration and exploitation for you, picking the right kernels, etc. All of this is completely obfuscated for you as the user. So the only thing that we need from you is essentially to say, okay, these are the parameters that goes into my model, and then help us go back and forth in this feedback loop. I hope this makes sense. Even though there is a lot of complexity going into finding the right strategy for doing optimization, all of that sits with us. Again, our job is to amplify your work. And one way in which we can amplify your work is by making the optimization process more efficient. So if you were to take one thing away from this talk, that should be it. We want to help you amplify your work by doing the most efficient optimization. And there is a lot more depth to what I just talked about. I don't know if you noticed, but there's a lot of references on the slides. Feel free, like we'll be sending those out, so feel free to dig into those. We have a lot of blog posts where we talk about some of these concepts. I can highly recommend it. But yeah, hopefully that gives everyone a bit of intuition about what's going into black box optimization in general, but also how this can be, how this fits in the context of SigOpt. And as I said earlier, you know, one of the things we hear a lot working in a variety of different industries is not a single metric represents success. And I believe that to be true, which is why we want to help you expand the optimization process to multiple metrics. And again, there is a lot of reasons why you should do it. Some of them are that it simply leads to better models, models which is closer tied to value. So again, let's take a step back to this interaction diagram. Again, we go back and forth in this feedback loop. And if you were to do multimetric optimization, at the end of the day, the only thing that you need to change is essentially the number of metrics that you're reporting back to us. So instead of saying, hey, help me optimize my Sharp, you can say something like, here is my profit and here is my risk. And why this makes sense, I'll talk about in a second. Or it can be, you know, if you're doing autonomous vehicles, maybe it makes sense to think about the performance of your models and the inference time. But again, what I'm trying to show here is that the only thing you really need to change is just the number of metrics that you're reporting back to us. So what does it mean to do multimetric optimization? Doing multimetric optimization essentially means that you have a set of competing metrics. And it's important that it's a set of competing metrics, because otherwise you're not doing multimetric optimization. And what I mean by competing metrics is that for every single point, or let's take a step back. When we do multimetric optimization, we're trying to come up with an efficient frontier of solutions that you can pick from. And again, this can be things like, on one axis you have the accuracy of your model. On the other axis you have the inference time. And the idea is, when we're trying to come up with this efficient frontier, every single point on this frontier is better in one direction. It's better than the other points in one direction. So this essentially means that you are willing to maybe give a little bit on the accuracy in order to win on the inference time, or vice versa. And this is why it makes sense for something like risk versus profit, and being able to make decisions based on this entire frontier instead of making decisions based on just the single number represented by the Sharp. Again, I hope this makes sense, that because these things are competing, there do not exist a single best point, which is why we're coming up with this frontier of solutions. So again, in the interest of time, I'll not dig into this, but there is a lot of references that talks about how these things are done. I will recommend digging into it. But in order to give you a little bit of intuition, the most simple way in which you can do multimetric optimization is through what is called convex combination scalarization, where you essentially, as we talked about before, we're trying to maximize a single metric. So if you have two metrics, let's just combine them and see what happens. But as you can see, there is this lambda value that controls how we're combining these metrics. And one of the things that we do under the hood, among others, is we're constantly changing this lambda value in order to try to come up with the biggest frontier that gives you the most points to choose from. Because at the end of the day, that's the problem we're trying to solve. Again, there's a lot more things going into it. I'll be happy to answer questions afterwards, or feel free to read the references. Because that's not the only thing we do. We layer in a bunch of other stuff. Another thing which makes sense to get a bit of intuition on is what's called epsilon constraints. Epsilon constraints is essentially us saying, okay, fix some value on the first of your metrics. Let's say the accuracy. Let's find a place that has an accuracy of 80%. And let's try to minimize the inference time as much as possible. That's kind of the question that you're asking, or that we are asking. And then we do that for all sorts of combinations. That's what you see. That's what the purple line here represent. Us trying to ask these questions and trying to come up with the maximum size of this frontier. Again, all of this is not something that you will see. It's just to give you a bit of intuition about what's going on. But as you could imagine, I talked about maximizing the size of this frontier. And there is probably regions that you don't care about, because chances are, if your risk is 0, you will not be making that much money. Or if your profit is extremely high, the risk is probably also very high. So trying to stay away from these regions makes a lot of sense, which is why as you do these optimization, like as you do multimetric optimization, we essentially allow you to specify, hey, what are the regions that I care about? Essentially say things like, I only care about profit if it's above 5%. And set a similar threshold for the risk, saying my risk has to be below a certain number. And now you're actually guiding the optimizer to faster find points that you care about. And that's what we're trying to show here with this gray line. Let's take a step back. Here, we're simply saying, try to maximize the size of this efficient frontier. And basically, the entire frontier is equally important. Now we say, try to stay out of this gray region, because I, as the domain expert, do not care about what I see in there. And of course, this is a stochastic optimizer, so we will end in there some of the times, but as you can see, we are a lot more likely to stay out of this region. And the reason why you should always do this is because it's free. When I talk about cost, it's not some sort of monetary number. It's essentially, what is the information that we need from you? And the information is, again, this feedback loop that we go through back and forth. And the cost here is the number of times that we have to go through it. But by you specifying what you want to see, we can actually get you to the results that you want to see a lot faster. So in that sense, it's free and no point in not using it. Again, this is just to give you a bit of intuition about what's going on. We do have a lot of joint work. Here's some with NVIDIA that I encourage you to have a look at. The same for the references in the presentation. They're all academic papers that kind of try to outline some of the things we're doing. So I know we're at the top of the hour, and I really do appreciate all of you taking the time to listen in to what I had to say. For those of you who have the time to stay a bit longer, I can see there is a few questions. So I will encourage you to put in more questions, send me emails, or listen in for the Q&A. Again, thank you so much for joining. I really do appreciate it.
Hey, Toby. So we have a question here. Can you go back to the epsilon slide?
Yep.
So the first question is, how is stability defined here?
Stability. That's a great question. I unfortunately do not know the answer on top of my head. If that sends me an email, I'll be happy to answer. Otherwise, it's in the references.
Okay, that sounds good. Another question is, do we have documentation or blog posts on this applied to trading and investing?
We do have some examples on our GitHub repo, and we do have some giant blog posts with 2 Sigma that I will encourage people to have a look at, which is essentially trying to outline as much as they can share. Again, you're the domain experts within trading. We're trying to help amplify your work through optimization. So yeah, we do have some. So that's the short answer.
Awesome, thank you. One last question. So how does SigOpt compare to open source? And is it predicated on one particular open source algorithm?
No, that's a great question. And kind of where it all started was through Mo, which is the Multimetric Optimization engine, which is built by one of our founders as part of his PhD, which was open sourced about, I think, half a decade ago. And that's kind of where it all started. And now we have built on top of that ever since and replaced everything from the original implementation by collaborating with people who from the community, by hiring the best researchers, etc. So it started out through the open source project, but it's no longer.
Okay, cool. Awesome. Thank you, Toby, for leading a great session. And thank you, everyone, for joining us today. So we're going to follow up with the slides and the recording. And any unanswered questions, we'll personally reach out and answer those as well. So our next session will be on Tuesday, April 22nd. Stay tuned for more info, and I hope you could all join us again. And if you have any additional questions, feel free to reach out to us.